Okay, so we're continuing our session. It's the last talk of the morning session. And the talk is given by Ordentlich from Hebrew University of Jerusalem, or educated, got all his degrees, undergraduate, master, and PhD from University of Tel Aviv. And he is now professor at Hebrew University, the Department of Computer Science and Electrical Engineering. So let's welcome.
Thank you. Okay. So yes, as you said, I'm an electrical engineer. So excuse me in advance for talking in peasant language about math. But my co-authors here are so Barak Weiss is a pure mathematician, and Oded Regev is a computer scientist. And actually, it was very fruitful for us to bring together different disciplines, each one as its own set of techniques, and somehow the combination of those resulted in this paper. And let me also use the opportunity to thank again the selection committee for choosing our work for this very prestigious award. Okay, so I'm assuming all of you have seen lattices before, but let me quickly give the definitions in any case. So a lattice L in Rn is a discrete subgroup of Rn. It can be identified with generating matrix or basis matrix, the same thing, G with columns G1 up to Gn, such that the lattice is G times Zn, or if you want, the lattice is the integer span of the column vectors of G. So in this illustration, this is a two-dimensional lattice. This is G1, this is G2, and the lattice consists of all points you can get by jumping integer jumps in each one of those directions, right? The scale of the lattice is determined by a quantity called the covolume of the lattice. What is the covolume? It is the volume of a fundamental cell. There are many fundamental cells for each lattice, but for this particular talk, we will like specifically this fundamental cell, which is the simplest one. It's the fundamental parallelepiped. And you get it just by multiplying the generating matrix G by the cube 0, 1 to the n. So you get this parallelepiped. It is a fundamental cell because if you move it next to each lattice point, you get a perfect tiling of space. This is what it means to be a fundamental cell. And its volume is obviously the determinant of the generating matrix G. Right, so the volume of a fundamental cell is the determinant, and we call this the covolume of the lattice. This determines the scale of the lattice, how dense the points are in space. Now, when someone gives you a lattice, the first question you will ask about this lattice is usually what is its minimum distance, or in other words, what is its packing radius or packing density. I will not talk at all about this question in this talk. But the second thing you will ask is what is the covering radius of this lattice or its covering density. And the main question is really in the lattice covering problem is we want to find the most economical way to cover Rn with balls centered around each lattice point. So let me be more concrete. Denote by B the n-dimensional Euclidean ball. We define the covering density of a lattice L, denoted by theta L, as the smallest volume of a dilate of the lattice, such that L plus this dilate Rb equals Rn. A picture always explains best. So this is our lattice. We start with putting a ball around each one of its points. And then we inflate the ball more and more until we reach a point where all points in space are covered. And the volume of the ball at this point is the covering density of the lattice. It doesn't matter. It's a ball because all I care about in the end is what it's the volume of the ball after I inflated it enough. So the scale doesn't matter here. Yes. It's the same ball. Oh, this is important. Yes, it's the same ball around each lattice point. It's just that the initial volume doesn't matter. Another question? Okay. Okay. Now, since if L plus RB equals Rn, and also alpha L plus alpha RB equals Rn for only alpha different than 0, I can assume without loss of generality that the lattice L is already scaled to have a unit covolume. So we restrict attention to lattices in this family of lattices, the family Ln that consists of all unit covolume lattices in Rn. And the main question is what is the optimal covering density theta n, which is the smallest covering density we can get among all unit covolume lattices. Now, I talked about Euclidean balls, but you can extend this definition naturally to any convex set. So for a convex set in Rn K, we denote by theta K of L, the covering density of the lattice with respect to K. And this is the smallest volume of a dilate of K, such that L plus Rk equals Rn. And similarly, we can ask what is the optimal covering density with respect to K. So this is the smallest covering density among all lattices with unit covolume. Now, an obvious lower bound for the covering density is 1. Why? In order for this to happen, I need Rk at least to cover some fundamental cell of the lattice. And fundamental cells has volume 1. So the volume of Rk must exceed 1. Right? So covering density is always at least 1. This is a trivial lower bound. So those are the two quantities we care about. Theta n is for Euclidean ball. Theta n k is for general convex body K. What was known about these quantities before our work? So for the Euclidean ball, everything more or less was known since 1959. So in this year, Coxter, Few, and Rogers showed that for any lattice, the covering density with respect to the ball is at least linear in n. And Rogers also proved that there exists a lattice for which the covering density is n polylog n. Right? So up to this polylogarithmic factor, everything is known for a long time ago. A few decades later, Griezmann closely inspected Rogers' proof, and he observed that Rogers didn't really need the full symmetry of the Euclidean ball in order to prove this result. Less symmetry is enough. So Griezmann defined some class of bodies that are symmetric enough, such that everything Roger does still holds. I will not give the exact definition to what symmetric enough is, but for this class of convex bodies, we also have this n polylog n upper bound on the covering density. And for a general convex body, what is large? Oh, so think about the density as the average. The density is the average time point in Rn is covered by balls, right? So if I move around Rn, for every point I count how many balls covered it. This average is the density, but you want not the. I mean, the average. It doesn't matter what the lattice is. It's always the same. It only depends on the volume of the ball. But you want every point to be covered, right? So you're asking what is the smallest volume of the ball such that all points will be covered. Yes. Yes. So you have your convex set, and you take the union of all its shifts with respect to all lattice points. And for the covering problem, it doesn't matter, right? You need everything to be, all points to be covered, right? So shifting K will have no effect on the covering. Okay, so this was the best upper bound before our work on the covering density of a general convex body. And it was also found by Rogers in the same paper. It was n to the log n up to constants. And our first result in the paper we published in JAMS that got the award was that actually for every convex body K, the covering density is at most Cn squared. Now, this means that for every convex body, we can find at least one particular lattice for which the covering density is small. But how hard is it to find these lattices? They're very rare, or maybe actually almost all lattices have small covering density. So next we ask questions about the covering density of a typical lattice. So of course, first I need to define what is a typical lattice. So I will use the standard definition from the literature. So SLNR is the group of n by n real-valued matrices with determinant 1. SLNZ is the group of n times n integer-valued matrices with determinant 1. As I said before, any lattice with unit covolume can be represented as G times Zn for some element G in SLNR. But this representation is not unique. Why? Because if I take an element T from SLNZ, then T times Zn is also Zn, right? So G times T times Zn spans the same lattice as G. So in general, a lattice is identified not with G, but with the orbit of G with respect to right multiplication in SLNZ. And therefore, the space of unit covolume lattices is equivalent to SLNR mod SLNZ. A measure mu n on Ln, the space of lattices, is called SLNR invariant if for any event in lattice space and any element G in SLNR, we have that the measure of GE is the same as the measure of E. So under SLNR invariance, basically all lattices were born equal. This is what we want. And it is known that there is a unique SLNR invariant probability measure, denoted by mu n, on the space of lattices. And we call this the Haar-Ziegel measure. Why? Because it is a Haar measure. And Ziegel is the one that showed that this is a finite measure. So it is a probability distribution. And that this is widely accepted as the natural distribution on the space of lattices. Right, so when I talk about a typical lattice, what I mean is a lattice drawn from this Haar-Ziegel measure. So now we have a distribution. We draw a random lattice from this distribution. And the covering density, theta KL, is a random variable. Right, so what is the first question you ask about a random variable? What is its expectation? Now, the answer is very disappointing. We show in the paper that the expectation is infinity, right? We're hoping that a typical lattice has small covering density, but actually the expectation is very bad. It's infinite. But that's not the end of the story, right? We can have random variables that are very concentrated around small values, but still have infinite expectation. What was the question?
Expectation is for each n.
The expectation is for each n, yes. Yeah, I mean, I don't know. Yeah, for n equals 1, there is only one lattice, right? But yes. Yes. So the question we ask is about the tail probability. What is the probability that the covering density of a random lattice exceeds some number m? So few people have looked at this before. Rogers didn't really look at this, but you can easily deduce from his result this bound that says that for V between 1 and n, and any convex set, the probability that the covering density of a random lattice exceeds this is exponentially small. Basically, a random lattice will not have covering density greater than 2 to 10 with very high probability. This is what this result shows. And in 2012, Strombergson improved this bound and showed that actually the probability that the covering density of a random lattice exceeds 1.756 something to the n is exponentially small. So you don't actually need 2 to the n. A smaller exponent also works. Our second result from the JUMPS paper studies this question. And we show that for any convex set and any m in the range n squared to n cubed, we have that the probability that the covering density exceeds m is bounded roughly by e to the minus m over n squared. So here are several corollaries from this result. First, our theorem 1 is a corollary of this. Why? You can choose m to be c n squared for some c large enough that will make this probability smaller than 1. And if the probability of this event being smaller is smaller than 1, then of course we have at least one lattice for which the covering density is less than Cn squared. Right, so this is a stronger result. Second, for any epsilon greater than 0 in any convex set, the probability that the covering density is more than n to the 2 plus epsilon is vanishing with n. And if you're not happy enough with vanishing error probability, but you actually want exponentially small error probability, if you take Cn cube here, you get that the probability that covering density exceeds this is exponentially small. So this improves the result of Stromberg's one with n cube instead of 1.756 to the n. Okay, these were the results. Now I'd like to tell you about how we proved this. Now I showed two theorems. One was for almost every lattice, and one was that there exists a lattice. I will only prove the simpler one, the one that says that there exists a lattice for every k whose covering density is small. Not that much is required to go from the proof of the existence to the proof of almost every lattice, and I will try to tell you as we go what are the missing ingredients, what else we needed to do to prove theorem 2. Okay, so we start with some convex body K. And as we've discussed before, the volume of this convex body, the initial convex body, is irrelevant to the covering density. So we can assume without loss of generality that its volume is V, and V is a number between 1 and C times n for some constant, right? And now our job is to construct a lattice L such that L plus some dilate of K will cover the entire space, right? So there are 5 steps in the proof. I will tell you each one of them one by one. The first one is almost perfect covering. So our first job is to find the lattice L with unit covolume, such that if I place K around each one of its points, in all my figures, K is a ball, but everything works for general K. So if I place K around each one of its points, I want that at least 1 minus epsilon fraction of space will be covered, right? Now the situation is completely periodic in the lattice, so what I actually need is that 1 minus epsilon fraction of this fundamental cell will be covered by shifts of K with respect to the lattice points, right? Now establishing this is easy. Why? Rogers proved a very long time ago that if I draw a random lattice L from the Haar-Siegel measure, then the probability that at least 1 minus epsilon fraction of it will be covered, of 1 minus epsilon fraction of the torus will be covered, is at least 1 minus epsilon to the minus 1 times e to the minus v. So if v is taken sufficiently large, this lower bound is positive, right? And this means that we can find such a lattice. Okay, so finding a lattice that covers most of the space is not hard. This is known. But of course, this is not enough. I want to cover the entire space. So what we will do, we will manipulate our initial lattice a little bit. We will make it denser in a smart way such that in the end it will cover the entire space. But it is hard to immediately aim at covering all points in Rn. What is easier to do is to aim at covering a discrete set of points. And if this discrete set is very dense, then once we've covered all of it, we're pretty close to covering Rn. So this is the idea. We define our discrete set this way. So P is a prime number, a large prime number between n and 2n. We assume n is large, and so this is an asymptotic result, right? So we can assume n is large. So this prime number is also large. And we define the lattice L2 to be our original lattice scaled down by a factor of p, right? So this set of red points, this is our L2. This is the denser lattice. And our goal is to manipulate L such that all points in L2 will be covered initially, and then very little work will be left in order to make sure we cover the entire space. Now, this L2 has a very nice relation to our original lattice L. Why? L2 is given by G, the generating matrix of L, times 1 over P Zn. And L is G times Zn, right? So L2 modulo L is equivalent to 1 over P Zn modulo Zn, which is equivalent to Fp to the n, or P is prime, right? So this is a finite field. So I can look at all the red points that fall inside this fundamental parallelepiped and identify them with elements of Fp to the n. How? The first index of each vector here is its coordinate in this direction. And the second index is its coordinate in this direction. Those indices are integers between 0 and p minus 1. So each one of those vectors, I can think of it as an element of Fp to the n. Now, some points so inside this fundamental parallelepiped, I have p to the n red points. Some of them are already covered, and some of them are not. The ones that are covered are the ones I like. The red ones that are not covered are the ones I need to deal with, right? So let's call the set of all points that are already covered A. Now, this is a set of points inside the fundamental parallelepiped, but I can think of it as a set of points in Fp to the n, because I already identified each one of them with element of Fp to the n. What do I know about the size of this set? Well, I have p to the n points inside the fundamental parallelepiped, and 1 minus epsilon fraction of it is already covered, right? So I expect about 1 minus epsilon times p to the n discrete points to be covered. Of course, I cannot guarantee this, but what is easy to show is that there must exist some shift of k, such that if I put this shift around each lattice point, then at least this fraction will be covered. Right, so I can, so let's ignore if I need a shift k, let's ignore this from now on. And I know that my set A has at least 1 minus epsilon times p to the n points. This means that its complement, ASC, has at most epsilon times p to the n points. Right, so this is my picture inside the fundamental cell. The cyan points are A. I hope you can see those in the back. It's a very poor choice of color. I'm sorry about that. And the red points are A complement, and the size of A complement is at most epsilon Pn. Now, the next step will be to choose some subspace of Fp to the n and add this subspace to the lattice in a way that will sort of kill all this hole. It will kill the red points, right? So what I'm looking for now is a solution to this discrete problem in Fp to the n, right? I'm looking for a linear subspace S in Fp to the n, whose rank or dimension is R, such that for any x in Fp to the n, x plus s is not fully contained in A complement, right? In other words, what I want is that basically if I shift this, for any subspace here, all of its shifts will touch the blue points. Once this happens, I'm guaranteed that if I add this subspace to the lattice, then all red points are covered. Right, so this is the discrete problem I'm trying to solve now. Now, the question is whether or not I can find such S, or what rank is required for this. And it turns out that answering this question, can I find such S or not, is completely equivalent to asking whether A complement is a Kakeya set of rank R, a discrete Kakeya set of rank R. Why? Here's the definition of a discrete Kakeya set of rank R. So a set G in Fp to the n is a Kakeya set of rank R if for any linear subspace S in Fp to the n of rank R, there exists some shift of some shift x such that x plus this linear subspace is completely contained in the set G. The most commonly known version of this definition is with R equal 1. In this case, a subspace is just a line. And a Kakeya set, a set is a Kakeya set if it contains lines in all directions, right? And x is the position of this line, right? So for every direction, I can find a position such that the line is contained in the set. In general, we can define K sets of rank R to be sets that includes shifts of all subspaces, right? So why are both of them equivalent? So if G is not a K set, this does not hold for every S, right? So there is some subspace S for which there does not exist an X for which X plus S is included in G. This means that for this particular S, for every X in FP to the N, X plus S will not be contained in a complement, right? So those questions are the same. Okay, that's cute. I renamed my problem with a different name. What do I gain from this? Well, what we gain is that there has been tremendous progress in the last 2 decades in understanding what is the minimal size of K sets. So this was a sequence of works initiated by Zev Dvir and then continued by other co-authors, including Zev Dvir. And the result we need from this line of work is this one. It says that if I have a set whose size is less than e to the minus, so I have a set in Fp to the n, in a finite field of coordinate P, f size n. And the size of this set is less than e to the minus n over p times p to the n, then this set cannot be a K set of rank 2. Okay? Now, the set I care about is a complement. I know that its size is less than epsilon times p to the n. If epsilon is smaller than, okay, my p is greater than n. So if epsilon is smaller than e to the minus 1, this means that AC cannot be a K set. And this means that I must be able to find a rank 2 subspace in Fp to the n for which this holds. Okay? So I have a subspace of rank 2 that satisfies what I need. How does it?
So the P, how big is your P? You take P linear in N?
P is linear in N, yes. And this choice, it's also needed. Yes, it gets me the n squared, but I also need this. I need P to be large enough such that the discretization argument works, right? So this choice is good for 2 reasons. Okay, so my figure is in 2-dimensional space, right? So the only non-trivial subspaces are lines. So to illustrate what it means to satisfy this equation, so this is my S, right? This is a line. And what I want is that each shift of this line will touch at least one blue point, one cyan point, right? Or in other words, it will not touch only red points, right? So this is one shift. This shift is good because it doesn't touch the red points at all. This shift is good. It touches 4 cyan points. This shift is good. It touches 1 cyan point. What is bad is not touching cyan points at all, right? So this shift is also good. Also this one, and also this one. So this set S satisfies what I need, right? Now the next step will be to use this subspace S that I've found in order to eliminate the discrete hole. So what we do next is we construct a lattice L1 such that L1 is a super lattice of L, and it is also a sublattice of L2. And L1 modulo L2 is equivalent to S. In particular, what we do is the following. G is the natural mapping from Fp to the N to the fundamental cell. And what we do is we construct L1 by taking G applied on the subspace S and adding it to L. Always easiest to understand with a picture. So this is our subspace, right? Now we embed it again in Rn, or inside the points of L2. And then we take this line, these 5 points, and we copy it around each lattice point, right? So we will copy it again and again, and we will get this new lattice. What is good about this new lattice? Well, I chose S in a way that will guarantee that once I add this to my lattice, all red points are covered. right? So maybe in the figure you see that some of them are not covered, but this is just because I didn't continue the lattice enough, right? So all points are covered. You can see this. So this is good. The bad thing is that the covolume of my new lattice L1 is now smaller than 1, right? I started with L that had unit covolume, but now I added P to the R points inside each fundamental cell. So the new covolume is P to the minus R. Now an important comment, I'm only proving existence, but if I also wanted to prove that almost every lattice has small covering density, then the way to do it is not to end pick S in a way that will guarantee that this equation will hold, but to draw S randomly and uniformly over the Grassmannian and hope that with high probability this will hold. So we show that this is indeed the case. We needed to extend a little bit of the Kakea results for this, but we proved that if you randomly draw S and the hole is not too large, you will get what you need. The other remaining ingredient is to show that if I draw L from the R-Ziegel measure, and I draw S uniformly, and then I construct L1 in this manner, then I get a random lattice. And this random lattice, up to scaling, is also distributed according to the R-Ziegel measure. Why this is true? Well, you only need to convince yourself that this distribution is SLNR invariant, and it's not so hard to show this. Okay, so now I'm in a situation where all red points are covered. Now a little bit is missing in order to finish the proof. So this is the last step, step 5, going from covering the red points L2 to covering Rn. So first we use this well-known fact also due to Rogers. And this fact says that if L plus K covers more than half of the space, then L plus 2K covers the entire space. Now remember, in step 1, I already chose L such that this covers at least 1 minus epsilon fraction of space. So if epsilon is less than half, I am guaranteed that L plus 2K covers Rn, right? So if I take this equation and divide it by P, then L divided by P is just L2. And what I get is that L2, the red lattice, plus 2 over P times K covers Rn. Okay. Now, I've already established that L2 is contained in L1 plus K. All of its points are covered by L1 plus K. So if this holds, then definitely L1 plus K plus 2 over PK equals Rn. And now is the first and basically only time that I use convexity of K. So since K is convex, then this Minkowski sum is equal to 1 plus 2 over P times K. And finally, I've mentioned that L1 has covolume that is too small, so I need to scale it up a little bit. So I multiply everything by P to the R over N. So now P to the R over N times L1 is a lattice that has unit covolume. So what I get is that this unit covolume lattice plus this dilate of K equals Rn, right? So my covering density is at most the volume of this dilate, which is P to the R times 1 plus 2 over P to the N times the initial volume of K. P is more than N, right? So this is at most E squared. And I get this upper bound. Now, remember that I needed R equal 2 in order for the Kakea argument to work. And P is a prime between N and 2N. So, and V, and I could take V to be a constant. All I needed from V is step 1. I needed almost perfect covering. This works with constant V. So plugging everything in shows that the covering density is at most constant times N squared. Okay, so this is the proof. How am I doing with time? I have some more time. Okay. So I will, are there questions till now? Maybe Before I move on, this is a good time to ask about the proof. Okay. So I would like to talk. What else did I use? Yes, I mean, okay. You also need to have that. When you scale up, when you multiply k by alpha, the volume will be alpha to the n times the volume of k. So I don't know, for some disjoint sets, this will not hold, right? So we also use this. But otherwise, this is the only place where we use convexity.
R equals 2 in the K way, because K will work with lines as well.
Yes. Yes, it works with lines, but if I go back to where I use it, yes. So to this result, for a line, you do not get a fraction. The fraction of p to the n you get vanishes with n. I think it was e to the minus n times p to the n. This is not good for us. We want to, yes. So Dvir's breakthrough was that the fraction does not vanish with p, right? For us, it's not enough. We also don't want it to vanish with n. So r equals 1 doesn't work. R equal 2 already works. Okay, so let me tell you a little bit about follow-up work we did with the same set of authors. So for the covering problem, we only want each point in space to be covered at least once by a ball or by K. But we can require something even stronger, right? We can ask for a lattice and a set K such that if I look at L plus RK, not just all points in Rn are covered, but all of them are covered roughly the same number of times, right? So we call this uniform covering. So let me show an illustration for what this means. So in this figure, the red points are the lattice points. And now I place a ball around each one of these lattice points, and I start to inflate the ball more and more until, well, at this point, this is the covering density, right? Now all points are covered, but the covering is not uniform, right? Some points are covered only once, some points are covered by 2 balls, some points are covered by 4 balls, right? So the picture is really not uniform in space. If I keep going and I keep inflating more and more, you see that the color map the trend becomes more uniform. And at some point, when I inflate enough, I will get an almost uniform color map, which means that every point in space is covered roughly by the same number of balls. So this is what we ask now. I want to understand what are the conditions for this to happen. So let us define this quantity, n of L, K, and X, as the number of lattice points that fall in K shifted by X, right? So equivalently to covering points, I can ask whether a ball around this point has lattice points inside it, right? If a ball around X has lattice points, this is equivalent to covering. And now I'm asking not just if it has points or not, but how many points are inside its shift of the ball, right? So this is NLKX. Now on average, if I look at this function and average it, let's say, on a uniform distribution over a huge ball with respect to X, then this will just be the volume of RK, right? We expect that from volume considerations that the number of lattice points will just be, that the lattice is unit covolume, right? So we expect the number of lattice points to be the volume of RK, but this may differ significantly, may vary significantly with X, right? But in average, we have this. We also know that if my ball or K is huge, if it's large enough, then the ratio between the number of lattice points that fall inside every shift of the set and the volume of the set tends to 1. This is as long as the covering radius is bounded, we can show this easily. It is well known, a well-known heuristic at least. So our question is really how large does the volume need to be for this to happen, right? So the covering will be almost uniform. So we define this quantity, eta of Rk and L, we call it the covering smoothness. This measures the basically the maximal deviation of this ratio from 1, where the maximum is with respect to all x in Rn. Now note that if this quantity is smaller than 1, it must mean that n is always greater than 0. Right, so having covering density smaller than 1 in particular implies that L plus Rk is a covering. So requiring that this is small is stronger than just requiring covering. And one subtlety is that if you recall the video I showed you before, so the trend is that as we increase R, as we inflate more and more, the covering becomes more and more smooth. But this is just a trend, and it turns out that this is not uniform in R. It's not uniform in how much I inflate. Right, so you can easily come up with examples where when I inflate a little bit, the covering smoothness actually, this parameter actually increases. Right, so you think of Zn and the cube. Right, so when I have my lattice is Zn and I have a cube, right? So at one point I will be perfectly smooth. If I take the cube as 0, 1 to the n, I will be perfectly smooth. If I inflate it a little bit, I'm not smooth anymore, right? So this is not monotone. So we can ask what is the minimal volume of a dilate of K, such that if I inflate further, no matter how much, the covering remains smooth, right? So this is this function. So we proved two results in the follow-up paper. It was submitted 2 years ago, but it was just published this year in the journal d'Analyse Mathématique. And the result is that basically if the volume of our convex set is more than n cube, then for almost every lattice, we will have smooth covering density with high probability, we will have smooth covering density. This epsilon measures how smooth we are, and this delta measures what is with high probability. And of course, those parameters affect the volume K we need for this to hold. And if we want that we want K such that no matter how much we dilate, we inflate it further, we are still smooth, then not much changes. We still get that we need the volume of K to be n cubed times some polynomial function of epsilon and delta. So that's all I wanted to say. Thanks for your attention.
Questions? Yes.
Maybe you mentioned, but I missed the lower bound for this problem for n square. The lower bound for n square. What?
No, I never said n squared is tight.
Yeah. So that's my question. So you didn't mention it. So what?
No, the only lower bound we know is Rogers, Coxter-Few Rogers. It's n, and it's only for the ball, right? Nobody knows. I mean, okay, you cannot have a general. I don't know, for a cube, for example, you can have density 1, right? So there is no non-trivial lower bound that holds for any convex set K, right? But for the only lower bound, the best lower bound we know for some convex set is Coxter-Few and Rogers, and this is attained for the ball.
Yes. But then there are very esoteric, like there are this counterexample to Borzug conjecture. You might imagine that there are these very esoteric convex sets which maybe do better, right? Like which are kind of don't cover themselves. But you know, they are quite esoteric.
That have small covering density smaller than n. Yeah. Yeah, definitely. No, I'm sure there are, right? Any lattice induces a convex set for the. I mean, take a lattice, take one of its fundamental cells, right? Definitely the covering density of this fundamental cell, which is convex, is 1. Right? So it is not known what is the hardest. I mean, in a sense, I don't know, the conjecture is maybe that the ball is the hardest convex set to cover with, but who knows. And if you ask me, I mean, I believe the truth is n, that we could only prove n squared, but I mean, I think it should be n, or n log n. Yes.
If you take a nice set like ball or simplex, do you know if this function is concentrate for large n is concentrated around the constant value? Like whatever you take any lattice, you have more or less the same.
Ooh. It's a very, very hard question, right? Because I mean, I suspect that the truth is around n, and all we could prove is that with high probability it's smaller than n squared. So yeah, I cannot say. I mean, okay, I would imagine it is, but okay. What is concentrated is the covering radius, right? So this is concentrated. But I mean, what we're asking about the covering density is basically the covering radius to the power of n. So I think I would guess it is not concentrated. I would guess the concentration is not that strong. But covering radius is concentrated. I'm pretty sure.
Any other question? Yes.
So your main result where you get this the bounds on the probability where you're outside of you're larger than m, the covering radius is bigger than m. So the covering radius, first of all, it's a proper function on
it's not my result is the covering density.
Density, sorry. Density. Yes, and I want to ask is, so the covering density is a proper function on the space of lattices.
Okay.
And there's, you could also take the length of the systole, the length of the shortest, like that's another, or the reciprocal of that is also a proper function. Do the results that you have translate to results about?
Well, so this is how we prove. Remember, I told you. Okay, I don't know why it's not working, but I told that the expectation of the covering density is infinite. So this really comes from this transference relation, right? You know that if you have a very short vector in the dual, then the covering radius is large. Yes. So we use this connection to prove. So yes, there is the probability that you have a short vector in a random lattice is not small enough, and this is why the covering density with not small enough probability is very large, right? So we do use this relation.
So that's also my question, that it is related to the statistics of the shortest vector, right?
It's through transference theorems, yes.
Because any unimodal lattice, for any dimension, there's a constant depending on dimension, so that there is a vector shorter than this number, right? And then when dimension is large, then you can ask how probable are that you're not typical. Yeah, it should be kind of related things. Yes.
Yeah, but by the way, a nice property of this Harzigel measure is that the dual lattice also has the same distribution, right? So there's another famous question, Butler, maybe some of you know it, whether there exists a lattice that has both covering radius that is small and both packing radius that is as big as we know. So our proof shows this, and it shows that there are lattices for which this is true also for the dual, right? Because with high probability, you get both of them for the primal and the dual. So then it's just a nice property of this distribution, that the dual and the primal have the same distribution. So if you prove something with high probability for the primal, it means that with high probability, you simultaneously get this property for the primal and the dual.
So maybe I ask again this question. So suppose there is a random variable for every lattice, so fixed dimension n.
Yes.
For every lattice, there is a shortest vector.
Yes.
Which is a constant, right? And then this is a random variable in space of lattices. And then you want to normalize it, subtract something, divide on something, and ask what will be the limiting distribution when dimension goes to infinity. Is something known about that?
I don't know. I mean, my
I think, yeah, but they're saying
No,
like
that
about Taylor. I'm asking about limiting distribution.
yeah, so I say it will. My guess it's probably constant. If you normalize it such that the effective radius
If you
is
normalize
1.
too much, yes, it's everything converges to
No,
zero.
not too much. I mean, everything should be normal. When you ask things about covering radius and the packing radius, you should normalize by the effective radius, right? The radius of a ball with unit volume, right? So the covering radius is close to 1 for a typical lattice. This is what we show. The packing lattice, of course, the packing radius, of course, we don't know, but probably it concentrates around 1/2. I mean, it doesn't mean, of course, that you cannot get better packing density than 2 to the minus n, but for a random lattice, I suppose this is what you get.
Well, I'm sorry I abused my powers of a chair, but let's thank our speaker again.